fugoid. And the fugoid was going up and down 2,500 feet per minute on average. Every time we went through one of these up and downs, we had a net loss of altitude, and we were getting closer and closer to the ground. When we fly an airplane, we try to maintain perfect balance. Smooth air, you can take your hands off and the airplane goes right where you want it to go. The wings are level, you don't climb, you don't descend. Everything is perfect, it's in harmony. In this case, engine number 2 is out of the equation. So we've lost basically a third of the thrust capability of this aircraft. We can do nothing more because the controls don't work anymore. They're gone. The airplane says, I want back what I had before. How can I get it? Okay, if we go down, we will build airspeed and we will get back to that harmonic situation I liked. So the nose falls and the airplane starts down, 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 looking for that speed. Speed builds up. The only problem is the process overshoots. Now it's doing 290. It says, wait a minute, that's too fast. How can I get back to 270? Oh, I gotta go back up. That'll bleed the speed back. So then we start up the hill. But it does it too much. And now we get down around 220. Oh, too slow. Let's go back down and get that speed again. The airplane was in harmony at 270 knots. It wants to go back to 270 knots. And in the effort to get it, it overshoots continuously, going too fast going down, too slow going up, and it sets in place this fugoid, this sine wave action, getting lower and lower after every occasion.
Every cycle
brought us lower, yes. We had up and down at 2,500 feet per minute. We had these great variations in airspeed, and the airplane was continually turning to the right. Now, this is not the methodology you want to come in for a landing. We're trying to get this wing level and keep it there. And how can we stop this up and down at the same time? It's a twofold problem. I don't want to get any closer to the Earth. We need to buy time to figure this thing out. We need to buy time to find out what this airplane can do. Because, quite frankly, in the previous 25 years to this event, there never has been a survivable loss of flight controls accident. Nobody's ever survived. If you're sitting at the gate at an airport, you can see an airplane that has engines under the wing. Maybe the wind is causing them to rotate around. Well, those blades you're watching at the very front of the engine are what's known as the fan stage. It's got a 300-pound titanium disc in the middle that's holding onto 36 fan blades. It's rotating up around 16,500 RPM. Metallurgical failure, that piece flies out. In a quarter of a second, all the blades, this mass inertia, exits through the side of the engine and out the side of the tail of the aircraft, throwing shrapnel everywhere. Those high-velocity parts impact upon the tail surface of the aircraft. They puncture through at great force. Beneath that surface, which you can't see, are hydraulic lines of very strong stainless steel tubing. Shrapnel basically sever all the lines. All the hydraulic fluid goes overboard, so we've lost all the hydraulic systems in a quarter of a second.
They're redundant hydraulic systems?
Correct. There's 3 systems. Say the elevator, one of the panels that move up and down in the back of the thing. 1 and 2 is on this piece. There's a separate elevator that's powered by 3 and 2. There's 1 and 2 here, 2 and 3 here. Okay? If I lose system 1, I still have number 2 powering this system, and I have 2 and 3 powering this one. If I lose 2, 2 goes away, but number 3 is not working out here. So I've always got something. On the face of it, good Lord, I mean, that's amazing. Triple redundancy, you're pushing the envelope, right? To expect anything worse than that to happen. Well, there's Murphy's Law.
Are there any cables?
No cables. If you look at the flight control surfaces of these airplanes, they're big as barn doors. They're huge. You have to use hydraulic advantage to operate these massive flight controls, both in weight and to fight the air forces that are against them. Well, if I can't have manual, then what do? Well, how am I going to replace the manual backup? Well, you put more hydraulic systems in there with redundancy. It's triple redundant. It's, that's good enough, We have resources at our command through radio. We can get patched in with a phone to what's called SAM. It's our maintenance people out in San Francisco. They know this airplane cold. They know all the systems. They have all the technical manuals. They have everything at their disposal. And if there's a backdoor way of pulling a circuit breaker or something to do, they can see this backdoor way of helping you out. The problem they were having was that whenever the engineer, Dudley Dvorak, called them, Dudley said, we have lost all our hydraulics. And they said, okay, we've got a communications problem. That can't be the case. 1 in a billion. Hard to believe. It's almost impossible to believe. Maybe no hydraulics in one system or no hydraulics in 2 systems. They couldn't believe there was no hydraulics in 3 systems. So Dudley said, listen to me. Number 1 hydraulic quantity, 0. Got it? Number 2 hydraulic quantity, 0. Number 3 hydraulic quantity, 0. Later on in post-accident, they said, we didn't know what to say to you because we were talking to 4 dead men. As designed, the airplane was no longer controllable. 2 problems we talked about, the airplane going up and down the phugoid and the airplane's roll tendency. It was an immensely difficult thing for me to operate the throttles to mitigate both those issues at the same time. So I was looking over all the controls and switches and everything that I had knowledge of in the aircraft, and they had executed just about everything I think I would have attempted. But in the DC-10, if the hydraulic systems fail, there's always an emergency methodology to get the landing gear to free fall done. They weigh many tons, and if we can simply open the doors, they usually just free fall out and they lock into place. Now the byproduct of that, that's a hydraulic system. When the gear is stored and they're up in the airplane, we've got trapped fluid in some of these lines. And I thought, if we could get the landing gear down, the very motion of the gear going down forces that fluid back into the reservoirs. Somehow, some chance, some of that fluid could be recovered, not go overboard, and perhaps they could get back the control of the aircraft. And we talked about it. But there's a golden rule in aviation. It's kind of an unspoken rule, but it basically says this. If you ever find yourself upstairs with minimum control of your aircraft, don't change its configuration. In other words, don't put flaps down, don't put gear down, just leave it the way it is. You know the devil you have now. If you change, you may not like the devil you get. You may lose control of the aircraft completely. So we had a discussion. Now, what are the merits of putting the gear down? If we put the landing gear down, are we going to lose it completely and the airplane's going to be a smoking hole in Iowa? We don't know. Is it better to land in a cornfield with your landing gear up or your landing gear down? There's not much test data on this. Is it better to land you on a 4-lane highway with the landing gear up or the landing gear down? There was interstate highways below us that we could have taken shots at. Is that a good idea? We don't know. Finally, the decision maker, Al Haynes, said, let's put it down. I don't think control-wise it can get any worse than it is right now. And besides, if it's down, it'll be a shock absorber when we hit. And so I executed the procedure to drop the gear. And we never did get back. The fluid evidently went right overboard again. But it seemed to me that the airplane was a little bit more stable with the landing gear down. I took my hands off the throttles long enough to put the harness and the seat belts on. And when I reached back forward, I put my hands back on the knobs.